Okay, so today's lesson is on the speed of light and its consequences. Okay, but first I have to explain, we haven't really talked about it yet, that light is a wave. Okay, this was discovered by Maxwell, James Clerk Maxwell, as a consequence of his laws, right? Maxwell's equations. Oh, I should have worn my Maxwell's equations, sure, but it's fine. But let's relate it back to a wave we're a little more familiar with, sound waves, right? Yeah. These are the pressure waves that result when I push air, like a speaker does. Have you ever looked at a speaker up close when it's operating? You'll see the speaker oscillating in and out. That's pushing the air. That's creating the sound waves that you're hearing with your ears. But let's think about the sound generated at the tip of an airplane. Okay? So here I'll draw a little airplane. There's wings. There we go. So you can think of sound as this wave propagating outwards like this, right? It's a little bit like if I drop a pebble in the water. It's going in all directions, and the sound's going in all directions here too, but I'm just drawing part of it. And we could track the distance, or the speed of the wave, as how far one of the wave, the peaks, or crests they're sometimes called, on the wave, how far it travels at a given time, okay?
Okay.
And that will have some speed. In air, the speed of sound is proportional to the square root of the temperature divided by the molecular mass, or the molar mass, of the stuff the air is made of. So it's got nitrogen, and oxygen, and argon. So you have to compute that molar mass. And then at a given temperature in kelvins, you would be able to calculate, with a couple of constants in there as well, what the speed of sound is. And it turns out it's about, I'm not sure, maybe 360 meters per second, which is somewhere in the neighborhood of 750 miles per hour. So it's pretty fast, right?
Yeah.
So if you have an observer standing on the ground and he sees this plane fly by, he'll see this sound generated, right?
Yeah.
And since the air is moving in the frame of the Earth, right? You have to remember the Earth is rotating, so the atmosphere is kind of rotating around with it. But the plane is moving with some velocity. We'll call it v sub p, velocity of the plane, when it's generating these sound waves. And it's moving through the air, so it's moving through that medium. So the speed of the sound waves that it's going to see, right, so v sub s prime, that's in the reference frame of the airplane, right, is going to be the speed of the plane minus the speed of sound, okay?
Okay.
Which means that if you go fast enough, right, you can get, so here we'll write fast, right, now our plane is really trucking. And what happens is the sound waves all pile up, okay, into one front. So, and this is what happens when the speed of sound, where the speed of the plane minus v sub s is equal to 0, right? So when the plane speed is equal to the speed of sound, right, it's the speed of sound in the reference frame of the plane is now 0. And so all the wave fronts are kind of piling up, okay? And you'll hear that on the ground. That's called a sonic boom. So anytime you cross over the speed of sound, the sound barrier as they call it, it's a big boom, breaks windows, it's really loud. Once you get past that, of course, the boom goes away, the wave fronts start looking like this, and this is not all that important. I was writing for illustration though. Here's my plane going really fast now, and what you end up getting are these wave fronts that trail behind like this, okay? I'm not sure that it's called a Cherenkov cone when it comes to sound waves, but it's in radiation, with electromagnetic radiation, it's called a Cherenkov cone.
Can you restate
So the faster it goes, the steeper this cone angle is, or the smaller the cone angle is, okay? So you go from this flat wave front to these wave fronts which come out like this, and the sound will kind of redshift, so it'll get lower in frequency. But that's not important. We can break the sound barrier. You can go faster than the sound is propagating, right?
Why does this make sound?
Oh, because the tip of the plane is, hitting the air, right? It makes a sound whenever you squish through the air. The engines, right? The engines make noise, and so that sound is, right? I'm just kind of making it come out of the tip of the plane. It's coming from the whole plane because the plane makes noise, okay?
Okay.
And those are sound waves. So this is how normally we think of speed with reference to waves, okay? Now the guy on the ground in all of these pictures, right? He sees the speed of sound always the same, v sub s, because he's not moving with respect to the medium, okay? The point is the speed of sound is in reference to the frame that this guy is in. It's like fixed, right? It's not the guy in particular, it's the fact that the guy is in the frame of the still air, if you will, okay?
All right.
So that's how it is for sound. Now, and you can kind of see it in the equations that you get, right? It says that the velocity of sound is going to be proportional to the molecular mass of something, right? In Maxwell's equations, right, there wasn't a medium that the speed of the light waves were relative to. It was a vacuum, but what exactly is vacuum? It's the absence of any material matter. So where is this vacuum frame? People had speculated or postulated that it might be this mysterious ether, which is this kind of frame of reference that everything in the universe sits in. But they unsuccessfully, they looked for it, but they could not find the existence of an ether. I'm not going to describe the experiment that demonstrated that. A proper interpretation, though, of Maxwell's equations and his laws of physics are that the speed of sound is the same in all reference frames. Okay? This was Einstein's interpretation of it, and it is the correct interpretation of it, but it has consequences. Okay? So the consequences are what we're going to kind of pursue. So we denote the speed of sound as c. That's like the symbol we use to represent it.
Yeah.
Actually, I don't know why. What the heck does the C stand for? I'll have to look into that. And it is equal to about 3 times 10 to the 8 meters per second. I think it's 186,000 miles per second. That's really fast. 186,000 miles, right?
Yeah.
That's very quick. But we are going to say that it's equal to 1. Right? It's easier to do relativity when c is equal to 1 because we can throw c out, okay? And it just makes the algebra easier. Now, when we do that, we have to think of all measurements of distance as being in some unit of time that some unit of space or distance that light travels at a given time. Okay, so if I say that my units of time are seconds, then my units of space would be light seconds. That's the length distance that light travels in 1 second. Okay?
Okay.
If you want it to be 1 and to use units that actually are valid, light moves approximately 1 foot per nanosecond. So you can use units of time in nanoseconds, which is 10 to the minus 9 seconds, and then your units of distance will be 1 foot. If we use seconds, right, light travels 186,000 miles in 1 second. So if we make our distance measurements in units of 186,000 miles, so x equals 1 is 186,000 miles, it's just really huge distances, okay? But just c is going to be 1. We're going to call c 1. So let me erase this. 1. And c is constant in all reference frames. That's our starting assumption. Okay? So everything we're going to talk about will stem from this fact that c is constant in all reference frames. Okay?
All right.
Now there's a little more motivation why this was done. So Newton's laws, right, are invariant under Galilean transformations, okay?
All right.
That kind of, is one of the justifications. We don't expect that the laws of physics are going to change if we rotate our coordinate system, right? It shouldn't happen, right?
Yeah.
Or if we do a physics experiment here, and then we try it over here at this spot, it shouldn't change, right, the results, okay?
All right.
Laws of physics should be the same in all reference frames. That goes for moving frames as well. If I do a physics experiment on a train moving at a constant velocity, I should expect the same result as if I perform the physics experiment on the ground. Now, this is kind of funny, though, if you think about it. Think about what we talked about yesterday, right? We put this guy, I'm going to write a kind of a abbreviated version of our train. We'll put a guy on it, right? And he's going to throw a baseball, right? So here's a baseball moving with some velocity u, and the train is moving with velocity v. And you will remember, and we'll call this u prime, because it's with reference to the train platform, right? So what is u? That's the speed of the ball in the platform frame, the guy that's standing still on the side of the tracks, right?
Yeah.
Well, you recall that would be equal to the velocity of the train, right, plus the velocity of the ball on the train, right?
Yeah. Yes.
But now, if we say the ball is actually light, and so we say, well, it's equal to c, because we know this guy is going to measure the speed of light to be c in his reference frame, so the ball is moving at the speed of light. How can I not say light? Then we end up, but also this guy has to measure speed c as well, right?
Yeah.
So c is equal to v plus c. Well, that only works if v is equal to 0, right?
Yeah.
So there's some strange stuff going on in moving reference frames, right? It's velocity dependent. If the relative velocity is 0, everything is fine. C equals c, that's normal, okay? So we're looking at some effect that takes place in moving reference frames that has to do with the velocity. I can draw a little space-time diagram of this, right, just to see what's going on here, right? So t and x, right? And then we'll draw the world line of this little train, right? And remember that whirl line is given by the equation x equals v times t. That tells me, pick a time t, this will tell me where the x point is on that, to draw this line. Okay?
All right.
We can think of this, since this is also where, this is the point where x prime is equal to 0, always, right? Because that's basically the origin of the moving reference frame being tracked in time, right?
Yes.
Well, what's the difference between this point here and this point, say, here? Well, this is the origin on the train, this spot right here where he's standing, at t equals 0, right?
Yeah.
This is the same point, x prime equals 0, at some later time, okay? And so for that reason, we can think of this whirl line as the t prime axis, okay? All of these points along here are where the origin is at different points in time according to the guy on the train's clock, okay? Does that make sense? Now, imagine that and since I said the speed of light is 1, okay, and I'm going to kind of leave this as an exercise, or we'll talk about it more in the next lesson when we talk about how to construct the moving frame axes in a Cartesian plot like a spacetime diagram, okay?
All right.
But it turns out that if c is 1, right, then that means that it's traveling, an equal amount in the time direction as it is in the space direction, right? So every time it moves 1 unit in space, it's going up 1 unit in time, okay?
Okay.
So that means to draw the whirl line of light, if you want to call it that, would be drawn at a 45-degree angle, okay? Because think about this. Here's the guy's whirl line. If he's moving slower, right, this line is less steep. It's closer to this line, which is where someone is standing still and just moving forward in time, right?
Yeah.
So this is the platform frame. He's not moving, so he's not changing his x position. He's just going up like this, right? So light, and that's not a very good 45-degree angle. It looks like it's less than 45 degrees. But we'll just use it anyway. Right? So let's look at a couple of points on here. I'm going to erase these details, and I want to look at this, okay? Now remember that, what does this point have to do with this? Well, this will be some point that the moving frame will measure the light at. And so this distance here, right, we're going to call it delta x prime, okay? That's the distance the light has traveled in the frame of the train, okay?
Okay.
Whereas this distance here, delta x, is the distance the light traveled in the platform frame, right? Can you see that?
Yes.
Yeah? This is just some point at which we're going to say, well, okay, how long did it take the light to get to this distance here? Okay, it'll be a different distance for the guy on the train, right?
Yeah.
Because his rulers are moving towards that point, right?
Yes.
They're moving in the x direction. But the time, right, as we've drawn all of this, is the same, right? The delta t is the same. And so here we've got that the velocity of light in one sense is delta x prime over delta t, but in another sense it's delta x over delta t. I call it delta t prime. Okay?
Okay.
And these have to be the same numbers, but we know they can't be, right? Because we're saying that delta t and delta t prime are the same, right? But that delta x prime is smaller by visual inspection than delta x, right?
Yeah.
So these two numbers cannot possibly be the same. And so that tells us that we have to change we have to do something about the way we draw our space-time origin, our axes, okay? We're not doing this right. This is the Galilean way of doing things. We're going to have to do it differently, okay? And so that'll be the topic of the next lesson. How do we construct a coordinate system that gets this right, okay? But I just want to point out that under the Galilean coordinate system, you get it wrong, because this can't be, right? These are two different numbers. Delta x prime is smaller than delta x, okay? Meaning that this speed would have to be smaller than this speed. But Einstein's saying they have to be the same. So we have to change things to make them the same, okay?
All right.
Now let's see what we can, without constructing the proper coordinate axes, we can, however, talk about the consequences of this constancy of the speed of light, okay? And we're going to look at two main effects, okay? The first one we're going to talk about the clocks on the train versus the clocks on the platform, okay?
All right.
And here's how we're going to do it. We're going to make a special kind of clock that Einstein invented called a light clock. And here's how it works. On our train, we're going to have this system. It's a little tower where this is a mirror, okay? This is a mirror, okay? And we're going to shoot a light beam up, okay? And it's going to go up, hit the mirror, and then reflect back down and be detected, okay?
All right.
And we're going to call that 1 second or whatever, okay? It's some delta t prime, okay?
All right.
The distance between this mirror and this detector and source at the bottom, okay, is a distance d. All right? Does that make sense? When you see the light going up and then bouncing off the mirror and coming back down again.
Yes.
And whenever it comes back down, that's kind of the end of our little second. Okay?
Okay.
And so we can say, well, all right, so that means that the distance to d, right, because d is the distance up, and then there's also the distance d back, right? So the distance to d is equal to c times t. So this distance to d is equal to the speed of light times this, this should be a delta t, by the way, times delta t. That's the time it took for the light wave to go from here to here and back again. Does that make sense to everybody? It's just speed times time equals distance, right?
Yes.
And since the distance it has to travel is 2 times d, and the speed that it's traveling at is c, the time it takes to do that is delta t, okay? That's how long it takes for our clock to make one tick. Yes?
Yes.
You understand, Gabe? Do you have a question?
It doesn't seem like a second.
It's not going to be 1 second. It's what we're defining as a unit of time, okay?
Okay.
It's equal to delta t, okay?
All right.
Now we're going to let c be equal to 1, okay? So I'm really saying that 2 times the distance is equal to delta t, okay?
Okay.
Now that's in the frame, in the train frame, right? That's what the train frame is going to see, okay? Let's look at the guy on the platform. What's he see? Well, I'm going to write out, t equals 0 here, okay? Here is the train. Here is the light clock, right? And the pulse is just starting off here, okay?
Okay.
At some time later, right, the train will have moved along to this point here, right? And the light will have reached the top of the mirror, right? But the path that we'll see it traveling is like this. You see that?
Yeah.
As it's moving along, we'll see it moving with it, right? This is like Galileo's experiment, throwing the apple off of the mast of the ship as the ship is moving by. The apple is moving with the velocity of the ship, right? So from the ground, it looks like that it falls some distance away and not merely at the bottom of the mast, right?
Yeah.
And then at a later time, it will arrive back down here. Okay, so we've got this triangle, right? And this distance, we're going to call this distance d prime. This distance here is just d, okay?
Okay.
As it turns out, there's nothing funny about the dimensions where there's no relative motion, right? To me, this distance, right, I'm not moving in the up or the down direction, neither is the train. So there's 0 relative motion in the up and down direction. So to both the observer on the ground, on the platform, and the observer on the train, this distance d is exactly the same because our rulers are exactly the same in those instances. Does that make sense?
I'm not sure.
Well, right, if you have a ruler here and I have a ruler here and you're standing still and I'm moving, you see our rulers are no longer aligned as I pass by, yes?
Yes.
But if you have a ruler like this and I have a ruler like this and I'm not moving in that direction, I'm only moving in this direction, then any point in space that I find and measure with my vertical ruler will agree with the measurements that you get for it on your vertical ruler.
Yes.
Because they haven't moved with respect to each other. The velocity in the y direction is 0. Okay?
Okay.
That's why. Does that make sense now?
Yes.
Okay. All right. So just out of curiosity, does anyone see where we're going with this derivation? What does this look like if you look at it for a minute? Does anyone see a triangle anywhere?
Yes.
Yes. And I want to focus on this triangle right here, okay? This triangle. What is this distance that I've drawn out here, right? Well, the total distance, right, will be, if this is t equals 0 and this is some other t later, we'll call that distance in time delta t, okay?
All right.
Because my delta t is the time from which I see the light signal start to the time I see it finish over here. So this distance is 1/2 delta t, okay? Now to convert that into physical distance, I have to multiply it times the velocity of the train, right? So the distance that I see here is just 1/2 v t delta t, right?
Yeah.
Yes?
Yes.
So that's this distance. So I've got a triangle, right? And this, of course, is a right angle, right? So we have the Pythagorean theorem, right? Which tells us that d prime squared is equal to d squared plus, I have to square this term here, 1/2 v delta t squared, which is going to give me 1 over 4 v squared delta t squared. Yes?
Yes.
Does everyone see that? It's just the Pythagorean theorem. It says that this length squared plus this length squared is equal to the hypotenuse squared. This is the hypotenuse of our triangle. This is one of the legs. This is the other leg.
Yes.
You square each of the legs, add them together. That should equal the square of the hypotenuse. That's the Pythagorean theorem. So, here's the Pythagorean. But, we can write the same thing here that we wrote here, right? 2 times d prime, I'll write it down here, 2d prime should be equal to c delta t. This needs to say delta t prime, by the way. Boy, I really mixed these primes up. Yeah, hang on, let me fix these. I should have put the primes only in the moving frame. So we should have called this d prime, this is d prime, because these are measurements in the trains frame, right? We just happen to agree with the d prime here, and so this would be d prime squared. There we go. Whereas d this is the distance that I'm observing the light to travel in the platform frame, right?
Yeah.
So here's what we're going to do. Let's take this equation. I'm going to multiply it all by 4. 4d squared equals 4d prime squared plus 4 times 1/4 is just 1, so v squared delta t squared. Okay? Now why did I do that? Because I can rewrite this equation as 4d squared equals, remember we set c equals to 1, so I'm just going to get rid of that. Delta t squared, right? Right?
Yes.
What do I get on this side, Gabriel? If I square the left side of this, what do I get?
4d prime squared.
4d prime squared, and that's going to equal, I got to square the right side too. What's delta t prime squared? Well, it's delta t prime squared, right?
Yes.
Okay, so why did I do that? Well, you see this value here, right? This allows me to introduce the delta t prime quantity into this equation, because 4d prime squared is equal to delta t prime squared. Here I have a 4d prime squared. You see it?
Yes.
All right, so let's plug it in here. 4d squared equals delta t prime squared. Again, why was I able to replace 4d prime squared with delta t prime squared? Because that's what it says over here. It's equal to that, yes?
Yes.
Plus v squared delta t squared, okay? Now look at this 4d squared. I can replace that. I should have replaced it all in one fell swoop. 4d squared is equal to delta t squared. You see that?
Yes.
Delta t squared, okay? Now I've got a delta t squared here and a delta t squared over here, right?
Yes.
So let's put the delta t squareds together. It's called collecting like terms. We do that a lot in algebra. I'm also going to flip the side that everybody's on. This says that delta t prime squared is equal to delta t squared minus v squared delta t squared. Yes?
Yeah.
But notice that I can factor out a delta t squared out of both of these terms here, right? So I have delta t squared minus v squared delta t squared, yes?
Yes.
All right, so delta t prime squared is equal to delta t squared times 1 minus v squared. See that?
Well,
I just factored out delta t squared. Now if I multiply it through, that'd be delta t squared minus v squared delta t squared.
yes.
Okay?
Yep.
And now what I'm going to do is I'm going to move this to the other side. Delta t squared equals delta t prime squared divided by 1 minus v squared. All right, now I can take square root, get rid of all those squares. I'm going to move up here, and we'll get that delta t is equal to delta t prime divided by the square root of 1 minus v squared. Okay?
All right.
Now, at this point, I'm just going to tell you, if I had not taken the c's out, if I left this as c delta t prime squared, or delta t prime,
Yeah.
if I left the c's in and not set them equal to 1, okay, then I would have gotten this. I've gotten that delta t is equal to delta t prime divided by the square root of 1 minus v squared over c squared, okay? That's just where it would show up if I had left the c in, okay?
Okay.
But, so now we think of velocities, right? So if we had a velocity that was equal to 1, that means that it would be traveling at the speed of light, okay? V equals 1 means the velocity is the speed of light, okay?
Okay.
What would happen to this equation if the velocity was 1? Gabe, can you tell me? If v is 1, what happens here?
Where we do 1 minus 1.
It's 1 minus 1 squared is just 1. So 1 minus 1 is what? 0? and I'm dividing by 0,
So,
right? It's undefined.
yes.
Goes to infinity if you want to think of it that way. So, yeah, that would be bad to go that fast, okay? But as we get close to that, right? So, typically what we do is we use this factor here. Gamma is equal to 1 over the square root of 1 minus v squared. And so we can write this as gamma delta t prime, okay?
Yeah.
We call this factor gamma, all right?
All right.
And the behavior of gamma is that gamma is always greater than or equal to 1. So what is that telling us? That is telling us that the moving clock, right,
Yes.
is moving slow. Right? Because the delta t prime, that's the time interval that this guy measures for this event that we agree upon. We agree upon when the light starts,
Yeah.
headed up, and we agree on when the light arrives back down. What we don't agree upon is how long it took. Okay?
Okay.
And it's not any kind of trickery or fakery. If you were on the side of the tracks and this train was going by, and there was a guy doing a dance, right? Instead of seeing him do the dance at full speed, you would see him kind of doing the dance in slow motion. Everything would be moving slowly. His clock would be ticking. Tick, 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 right? Everything would appear slow if he's going fast enough. Time slows down
If you go fast.
if you go fast. And this is by how much it goes down. Okay? So, the time between events that happen at the same place, okay? Do these events, this and this, happen at the same place? No. This event happened here in this frame and over here in this frame, okay?
Okay.
Do the events of the light leaving and then coming back, does that happen at the same place in this frame? Yes, it does, right?
Yes.
So here, this event of the clock ticking all happens in one spot, okay?
Okay.
And time, the intervals of time measured between events that take place at the same spot, right, that is called proper time, and it will always be the smallest interval of time, okay?
All right.
So the guy on the moving train will say that this clock tick that happened took a small amount of time compared to what I think it was, okay?
Okay.
An object moving by, their clocks, if there are people on the train holding the clocks up, as they're passing by and I'm standing on the tracks looking at it, the faster they go, the slower these clocks appear to move to me. I mean, you know how fast a second hand ticks on a clock, right?
Yeah.
So it's literally tick, tick, really slow, okay, if it's going really fast. The faster you go, the slower time moves, okay?
Okay.
So proper time intervals are always the least, okay? The smallest time intervals. I'm going to erase this stuff. And I want to talk about something similar that happens, but with space, right? Because we agree on the relative velocity. The guy on the train sees me moving back past, the guy on the train sees the guy on the platform going that way, right? At the same relative velocity as the guy on the platform sees the guy on the train moving that way. They don't disagree on the relative velocity. So V of the train, right, is agreed upon.
Yeah.
But they think the times are different, right? If that's the case, then the distance that they think has been traveled between, if we put a ruler out here, let's see, I've got to draw this a little bit differently, don't I? I'm going to draw it like this. If we laid down a ruler on the platform, okay, and here's the light clock, right, just at the start of its tick, right, and this is kind of the zero of the ruler, right, and then some time later, right, he's traveling at velocity v, draw the ruler again, here was that 0, and now the light clock is here at the end of its tick. It just arrived back down at the bottom, right? So we get this distance here, right? And we can call this distance L in the platform frame, but we'll call it L prime in the train frame. That's how he would measure it, okay? He would measure it by saying, okay, well, at this point the zeros and the zeros are aligned. Later at this point, he'd have to have this other car back here, right? He would observe this distance here, right? And this is L prime, okay?
Okay.
And so what we can say is that the guy in the platform, right, would say, okay, well, the length of this rod, where at the origin is where the rod starts. I should really just make it one rod, shouldn't I? And the end of the rod is at the point where the light returned, right?
Yeah.
Will be equal to the velocity of the train times this delta t, this time I measured for the light to go up and then to come back down, okay?
Okay.
Now remember, this is a longer time in the platform frame. the guy on the train will say this distance L prime is equal to the velocity of the train, which he's going to see as the velocity of the platform moving in the opposite direction, right?
Yes.
Times delta t prime, which is a smaller time, yes?
Yes.
Well, from before, we had, I'll just write it up here again, that delta t was equal to gamma delta t prime, right? Gamma is always greater than or equal to 1, which means that delta t is larger than delta t prime. Delta t prime is smaller than delta t, okay?
Okay.
I'm going to replace delta t prime. I can rewrite this as delta t prime equals delta t divided by gamma. I just divide the gamma out to the other side, right?
Yeah.
And then I can substitute in for delta t prime right here. So this is equal to v delta t divided by gamma. But v delta t, right, this little piece here is just L, right? And so I get L over gamma. Now remember that gamma is always greater than or equal to 1, right?
Yeah.
So since gamma is greater than or equal to 1, this implies that L prime, right, if you divide by something that's always greater than or equal to 1, that means that L prime will always be less than or equal to L. Okay?
All right.
It's equal to when the velocity is equal to 0. Okay?
Okay.
Because then gamma is just 1. Because the square root of 1 is 1. Right?
Yeah.
But if the velocity is a large velocity, something close to the speed of light, right, then gamma will be bigger than 1. Okay? It might be 20. Okay?
All right.
And so now L prime is L divided by 20, right? So what that means is that moving rulers contract, okay? So if you were to stand and watch an object move by, right,
Yeah.
at a high speed, uniform velocity, it would appear, in the direction of motion only, I add, right, it would appear to get squashed in the dimension that it's traveling, okay? So if the train car at rest looked like this, right, that's at v equals 0, at some very high velocity, the height would be the same, but the width would be much smaller. This is v much, much greater than 0, okay? Some very high speed. The train gets squished, okay?
All right.
Everything looks squished. And that just falls from time dilation and the concomitant length contraction that takes place as a result of it, okay?
What if this train was a solid piece of metal?
Gets squished.
Where would all the metal go then?
Well, interestingly, if you had something on the side of the tracks that could detect the density of metals, okay?
Yeah.
Then as the train went by and the density, since you're taking the same amount of metal and squishing it into a smaller volume, right?
Yeah.
Because you reduced the dimension in one direction. Remember, the height will stay the same, but in the direction of motion it gets squashed, but the same amount of matter is in there, right?
Yes.
The density is increased. You would have if you had a meter that could measure density of things passing by you, it would measure an increased density.
Okay.
Turns out that what we know as magnetism is kind of a result of this. It's really the electric charge, okay? But seen from a reference frame where it looks like the charge density is greater because the distance has been squished down. So you've got some number of electrons in a unit distance, but now we decrease that unit distance, so the number of electrons per unit distance has gone up from my reference frame. And that's what we know as the magnetic force. And I don't think we'll get into that this year, but that's one of the consequences of it. The last thing I'll mention is that, like, well, can this possibly be real? Yes, we've done experiments with atomic clocks. We put them on planes and fly them at high speeds and bring them back together, and we see that one of them is ageless. They're not, synchronized anymore. And they record the calculated intervals that they should, given the speeds that they go. Okay? But here is an example. It can be somewhat interesting, I suppose. There's a kind of an experimental result. Oh, and before we move on, I should mention that proper length. I mentioned proper time, right, is this the interval of time measured between two events that take place at the same spot, right?
Yeah.
Proper length is defined as length in a reference frame in which the measuring rods are stationary. They're not moving, okay?
Okay.
And they will always be the greatest length, okay?
All right.
So proper time is always the shortest interval between two events, and proper length would always be the largest distance between 2 points, I guess. I'm not sure how to say that, but now I want to talk about muons. Okay, muons, it's a type of particle. It comes from the decay of pi mesons. Basically, cosmic rays, right, from outer space, impinge upon our upper atmosphere, and they create these muons. They're made, okay, in the upper atmosphere, though. Okay.
Okay.
And we've made them in the lab as well. And in the lab, we can do it in the rest frame, in the frame of the muon itself. Right? And we've measured that the lifetime of the muon, the time that it lives before it decays into something else, is about 2 microseconds. Right? And so if you say, well, you know, if I want to know how far will they travel, right, if their lifetime is 2 microseconds, right? And I think you can say their mean velocity coming into the atmosphere when they're created up in the upper atmosphere is somewhere in the neighborhood of, I think it's 99.8% the speed of light, so they're really trucking. They're going fast. Right? So you say, okay, well, their lifetime is 2 microseconds, right? How far do they travel, right? The distance they're going to travel from the upper atmosphere downward, right, is going to be their speed, velocity, times their lifetime, delta t, how long they live, right? Before they decay into something else, right? And if you use these values of 2 microseconds, which is 2 times 10 to the minus 6 seconds, times, oh, that's not the speed, that's the lifetime. The velocity, 0.998 c times 2 times 10 to the minus 6 seconds, right? This is somewhere in the neighborhood of 600 meters or so, okay?
All right.
But we observe them down on the surface of the Earth with a greater frequency than we ought to, if that's their lifetime. And it turns out that relativity can explain this, because, and we'll call this delta t prime since it's in the frame of the moving muon, right? What is delta t in our reference frame, stationary here on the surface of the Earth? Well, it's gamma times delta t prime, right? Which we plug the numbers in, right? We would get 2 microseconds divided by the square root of 1 minus 0.998. If we use it in 0.998 times c, then this will divide out the c in the bottom, and so we can just square that number, right? And if we calculate this, this comes out to be about 30 microseconds. And if we say, well, what's the distance then? Right, so I'll call it d prime. The distance that we would observe, so this is what the muon thinks it's done. It thinks it's traveled 600 meters, and it thinks that its lifetime was 2 microseconds in its frame. People on Earth observe this lifetime to be 30 microseconds, right? And the distance it travels, right, that we observe is closer to 9,000 meters, okay? Which explains why we see so many muon decay events at the surface of the Earth, okay? So that's a real, like, experimental result that, you know, kind of in an indirect way confirms. You could have predicted, I don't know that they did predict it, but confirms anyways an experimental result that we see in particle physics, okay?
Okay.
So, the two things that we described, and we'll see it again, we'll do it in a more formal way when we develop a set of transformation equations that work for Einstein's relativity, okay?
Okay.
But this result with clocks we call time dilation. All right, this is what delta t prime is equal to gamma times delta t. No, I should do this way, that's what I thought. Delta t is equal to gamma times delta t prime, where prime is always, for us anyway, is going to be the moving observer. And then length contraction, which is L prime, equals L over gamma. Okay? There's one more kind of sweeping general consequence in special relativity that has to do with simultaneity. It's called the relativity of simultaneity, but we're not going to talk about it this time. We'll talk about it later. I think we'll probably next move on to generating the coordinate system. How do we figure out what that is? Well, actually, no, we will have to talk about simultaneity then first. Well, we'll figure it out when we get there. But simultaneity, you know what simultaneity means? You know what simultaneous means?
Yeah.
If I see something happen at the same time, right?
Yeah.
I say they're simultaneous. Yeah, so things get really funny with relativity and simultaneity. Turns out that reference frames, moving reference frames, will not agree about events being simultaneous. So that's another big sweeping consequence of this. But these are two of the most striking results, okay? Explained in kind of a general way, but we can do it more formally using the correct transformation equations, right? The right ones, but we'll have to derive them. And they're not that hard, to be honest. Once we have them, we can use them, though, to calculate lots of stuff. But more importantly, we want to generate these pictures, because it's really, you want to use, when you solve special relativity problems, you want to solve it with a picture,
Okay.
right? If you need to actually calculate a number, you want to use these transformation equations, but you really want to be able to draw the pictures that show what's going on. And then you can reconcile correctly most of the strange things that happen in special relativity. Okay, so hopefully we'll be able to do that. All right, that's it.